Okay, let's have a look. Here we go. Okay, so how are we gonna approach this? What do you think? Hunter, what's our first, Raj, you're taking a bite there. What are we gonna do? What's our process here? We're gonna find dy dx. You wanna solve for y?
Well, would it be easier if you factored out like an x squared and a y squared? Like pull it off to the side?
Well, see, you can't factor them out because they're not common factors, but even if you could, let's just talk about that. What if we had, let's say, a common factor up there? If I factor that out on the left, then all of a sudden what used to be a kind of a relatively simple term-by-term differentiation issue now becomes a product rule. Yikes. Okay, so no. So do we want to solve for y here? No. Emphatically, no. We probably can't anyway, right? So what's our strategy going to be?
Differentiate.
What's it going to be?
Differentiate.
Differentiate. And what's our new fancy word for this process? Yeah, good. We're going to implicitly differentiate, meaning we're just going to differentiate using the chain rule. Differentiate everything with respect to x. And so when I've got x's up there, when I differentiate with respect to x, it's easy. That's like the old stuff, right? The derivative of 6x squared is what? 12x. Done. That's it, right? Okay, but whenever we differentiate a term that has a y in it with respect to x, what are we always going to get out of that at the end? Y prime by the chain rule. Good. So we're going to implicitly differentiate with respect to x. And really that just means we're going to take each term, because this is just a term-by-term situation. So that part's easy, and see what we get. So what do we get? What is the first term going to give us when we differentiate implicitly? 2y, y prime. Good. Okay, now this one's a little harder. What about this one?
6x 2y.
With the brackets.
Okay, good. This is going to be, and we have to always look when we're differentiating. Differentiating, you're going to, I know we're still kind of learning this, but in the not too distant future, you're going to look back and say, really, differentiation is just following rules. And once you learn the rules and you learn to kind of, when you're inspecting an equation that you're differentiating or a function, when you learn to recognize which rule applies first and which one applies second, which you'll get, right away you'll get, then it's not that bad. So what is the rule that's going to apply here? Right. You're right. You were saying the right thing. Product rule, right. So we've got this constant of 3 that's out front, and then we've got to find the derivative of that product, right? So product rule. We might as well just do like the first factor times the derivative of the second to get things rolling, right? So first, what's the derivative of the second?
2y.
2y, y prime, good. Plus, second derivative of the first? 2x, good. So then, how about this guy? Minus
4x cubed. But it's plus.
Okay. Equals 0. So now what's left to do? Simplify and then just solve for y prime, right? So we could simplify by maybe distributing the 3, and we're going to get 2y, y prime plus, what's this term going to be? 6x squared. Okay, plus, okay, minus 4x cubed equals 0. Okay, now here's the part where I think you can do this in one step. I really do. I think you can do this in one step. No, think about it. If you kind of map it out ahead, you really can, because what are the steps we're condensing? The steps that we're going to condense into one here are we're going to get all the y prime terms on one side. The non-y prime terms we subtract to the other side, right? So it changes the signs. We're going to factor out a y prime and divide by the remainder, right? So no big deal. We can do that. So we're gonna get a y prime equals. Now, the numerator on this side is gonna be all the non-y prime terms that get pushed to the right, isn't it?
Yeah.
Agreed? So what are those gonna be? Let's see, there's a non-y prime term and there's a non-y prime term. So yeah, if we wanna put the positive one first, you don't really have to, but if we do, this one becomes positive, so we'll put that first. That one's gonna become negative, so we'll put it second. And those are on the other side, right? Okay, all the y prime terms, which are just these guys then, are the ones that are gonna be left on the left side, correct?
Yeah.
And we're gonna factor out a y prime, and whatever's left over is just gonna get divided away to the denominator of the other side. So what's left over?
2y.
Yeah, this is gonna give us a 2y plus 6x squared y. That's our answer.
Wait, can't I cancel the 6x?
No, you can't cancel anything because I can only cancel like factors. There's one thing we could do.
2x.
Good, we could divide both the top and the bottom by 2. And that would probably be a good idea. But it's not like it's really dramatically changing anything. So we get 2x cubed minus 3xy squared over y plus 3x squared y. Okay, yes sir?
Why do you only get one y prime, like over on the left?
Because the step that we skipped was we factored out a y prime. So let's just add that real quick. Right, so on the left side, if I factored out a y prime, what would have been left? Well, I would have had a 2y plus 6x squared y, which I'm just going to divide away from both sides so I get it on the bottom.
Yeah, I mean,
Okay? So I know that's a lot of stuff to compress into one step, and this kind of flies in the face of maybe some stuff you've been told in the past about showing all your work, but we're kind of past that stage. There's a lot of research that shows, I've probably mentioned this before, there's a lot of research that shows that the kind of thinking you do and the kind of connections you build in your brain when you do mental math, those are the very same ones that you use when you do algebra. So you actually strengthen your algebra ability by compressing steps and doing some mental math. Okay? All right, so let's finish up where we left off yesterday.
You should tell that to our middle school and our elementary school teachers.
What's that?
You should tell that to our elementary school.
I think maybe that's not a bad idea as long as you had like groups of students that are, I think it's not good for everybody. It's really good for you guys, but it's maybe not right for everybody. So here's, now let's go back and kind of catch up with where we were yesterday. This is a good problem. I'm gonna draw a picture at the end and we'll see this in action, but I want you to, we gotta kind of recapture where we were yesterday, because this is an important one. You're gonna be doing a lot of stuff like this from now on.
But we got the answer.
We didn't quite, we got one answer, right? So remember what we did. We started off with this relation x squared plus y squared equals 4. And we'll look at the graph of that in a second. We'll kind of put this in the context of a graph. We wanted to find all of the tangent lines to this relation when x equals the square root of 2. Okay, so think about that now. Let's just, before we go any further with this, let's kind of build a mental picture, think of a process. When we're trying to come up with the equation of a tangent line, the recipe for a line just means we need a point and a slope, right? Okay, and so in the past we've done a lot of this stuff. The point is non-calculus stuff. The point comes from just evaluating the function at a certain value of x to find the corresponding y value, right? No big deal. Calculus allows us to, by taking a derivative, if we evaluate the derivative function at that value of x, then it's giving us the slope of the curve at that point, right? And that's the other piece we needed, was the slope. So then we've got the point of tangency, we've got the slope of the line, little algebra 1, and we've got the equation of a line, right? Okay, the difference here was, though, okay, first of all, let's just find the point, right? Well, it turns out to be 2 points this time. if I evaluate my original, I can't say function this time because it's not a function. If I evaluate the original relation when x equals the square root of 2, look what happened. We got, I guess I need to draw some lines. So we did this. We went from here down to there. Right? When we plugged in x equals the square root of 2 into our original equation, the square root of 2 squared is 2, right? So we got 2 plus y squared equals 4. Solving for y gave us two different answers, right? So that told us something important. That told us that for this relation, when x equals the square root of 2, there are two corresponding y values for that one x value, right? So is this going to pass the vertical line test then? It's not for sure, is it? Because we already know one place where it fails, at the square root of 2. When x equals the square root of 2, there are two overlapping y values, right? Okay, so then we've got to say, all right, so first of all, we know right away that I'm going to have two different tangent lines because I have two different places where x could equal the square root of 2. One of them is the point square root of 2, positive square root of 2. One of them is x equals square root of 2, y equals negative the square root of 2. Okay. Now we got to go down and look at the derivative part of this. So we take the original equation and we implicitly differentiate it, right? We took the derivative of the first term gave us a 2x, second term gave us a 2y, y prime, derivative of 4 was 0. We solved for y prime, and we got y prime equals negative x over y, okay? So then we've got to use that formula to calculate the value of the derivative at each of our 2 points then, right? Because the x and y values are going to be different at each one. The x values are the same, but the y values are different. So really yesterday, we got through with half of it. We dealt with one of the 2 points. If we take the point square root of 2, square root of 2, well, when we substitute, we get the derivative y equals negative 1, right? Then we did our algebra 1, right? Y prime equals negative 1. Then we solved for b. Right, we knew what m was negative 1, but we plugged in the values of x and y and solved for b, and we got 2 times the square root of 2. And so then when we plug in the value of m and the value of b, we got the equation for that line. So there's one of our 2 tangent lines. Right, now let's find the other one. So the other one, I'll use good festive holiday colors here. So the other one, when x equals the square root of 2 and y equals negative the square root of 2, what is y prime going to equal? Yeah, I'm going to get negative, was it x over y or y over x? Can't remember. X over y. So I get negative minus the square root of 2 over the square root of 2. Negative times a negative is positive, so I get 1. Good. So then I've got to solve for b. So same as before. I'm going to get my y value, which is this time negative the square root of 2, equals m is 1 times x was the square root of 2 plus b, right? So negative radical 2 equals radical 2 plus b. So what's b equal to? Yeah, negative 2 radical 2. And so our other equation ends up being then y equals 1x plus negative 2 radical 2. Okay, does that make sense? Well,
Could you scoot up just a tiny bit?
sure.
Thank you.
Is that far enough?
What's behind the plus?
Let's see. There you go. Let's look at the graph of this. See if this makes sense. Okay, so that look pretty centered right there? Close enough? No, bad. Oops. How's that? Good? Okay. Good enough. Down a little bit? Oh, you know what I just did? I just made it. There we go. Close enough. Okay, so if we took, now think about this, if we took an x value of the square root of 2, that's about 1.414, right? So that's going to be right about there-ish. That gives us 1 point there and 1 point there. Makes sense now, doesn't it? What were the coordinates of these? This was square root of 2, square root of 2. This was square root of 2 minus square root of 2. Okay? All symmetrical like it should be. When we graph the tangent lines, makes sense, doesn't it? Right? Think about the equations of those. This one up here would have been y equals negative x plus 2 radical 2. This one down here would have been y equals x minus 2 radical 2. Y-intercept, yeah, it's about 2.8, isn't it? I mean, if I drawn it right. That's about negative 2.8, roughly, 2 times the square root of 2. The slope is negative 1, the slope is positive 1. Now we can kind of see that, yeah, it worked, right? Those are the two tangent lines that we calculated. Yes, sir?
Is there any significance to the point which the two change?
I mean, maybe. Maybe. If, depending on the context, there could be. Yeah. Okay? Make sense?
Yeah.
Okay. I'll put the assignment up. You can work.